Welcome to the video on stereochemistry. Finally, before we get into the deep trenches of stereochemistry, we must review the term isomers. First, we have constitutional isomers, and those are the isomers that have the same molecular formula but have a different structure. They actually have a different name, so they're completely unique compounds. Alternatively, and in this chapter, we will talk about stereoisomers. Stereoisomers have the same molecular formula and the same general structure, but they have a different spatial arrangement. The way I describe that is each carbon has the same things attached. It's just maybe in a different orientation. And so that's stereochemistry. So if we get a little deeper into the specifics, right? So here we have our constitutional isomers, but then under the term stereoisomer, we have enantiomer and diastereomer. And those are the two things that we're going to talk about in this chapter, enantiomers and diastereomers. For a quick definition, enantiomer is a stereoisomer that is non-superimposable on its mirror image. And enantiomers are often also referred to as being chiral compounds. Diastereomers, on the other hand, are stereoisomers of each other. So that means they are not the same compound, but they are also not mirror images. And we'll get into the details of that as we move forward in this chapter. In terms of cyclocompounds or rings, we have this example where we have our two methyl groups on the same side of the ring. We call that cis, and the two methyl groups on the opposite side of the ring, and we call that trans. This is an example of a stereoisomer, and specifically, they are diastereomers. And remember, the IUPAC name is going to include either cis or trans at the very beginning of the name. When we have a double bond, we can also have this idea of cis or trans. So we have both methyl groups on the same side, that would be cis, methyl groups on the opposite side, that would be trans. And again, that cis or trans needs to be in the name. We've talked about the E and Z designation, which is a more advanced way of doing the cis and trans. That designation is going to be put at the beginning of the name. Identifying which kind of isomer we have is going to be a very important part of this chapter. Constitutional isomers, stereoisomers, or identical structures. And so let's walk through. The answers are given. In this top example right here, I hope that you see that that is simply a ring flip. We have an OH in the equatorial, and now we have an OH in the axial. So that is simply a ring flip, and so that's going to be considered identical. These two molecules right here would be considered conformational isomers. For the next example, we have a chair conformation. We have this OH that's axial and this OH that's equatorial, and that compound is actually cis. See how both groups are heading up from the ring. In the second compound, we have this is axial and this is axial. So one of those stereocenters switched, and now we have what's called trans stereoisomers. And again, you can see the OH, one's going up and one's going down. And the bottom comparison down here, we have a cyclocompound with an oxygen and a double bonded oxygen. So each of these have 1 degree of unsaturation. We just have to make sure we have the right number of carbons and hydrogens. And each one of those actually has 4 carbons and 8 hydrogens and 1 degree of unsaturation with 1 oxygen. So those would be considered constitutional isomers. Same molecular formula, different compound. I'm going to let you try these two here on your own. Confirm that these are identical and these are stereoisomers. So if we focus now on our description of enantiomers, we are going to be talking about chiral molecules. A chiral molecule is an object that is asymmetric, which means that it is not the same as its mirror image. The best example of this is going to be your hands. Your right hand and your left hand would be enantiomers of each other. They are non-superimposable and they are mirror images of each other. I think you can very easily see that our hands are chiral. There is no way we can superimpose them. But if we look at them, they actually are mirror images of each other. Here's an example of a chiral compound found in nature. Limonene is found in oranges, and it has a chirality center right there with this branch coming towards us. The enantiomer is found in lemons, and that has that branch going back away from us. So these two compounds are enantiomers of each other. They are chiral compounds, and they have a very different effect on the receptors in our nose and for our taste, the difference between oranges and lemons. So how do we get an enantiomer in chemistry? The easiest way is to break it down to have a single carbon with 4 different groups coming off of it. And so if we have the mirror image, so you can see the blue is here, right? and then the green and the white and the red all follow. So it is the mirror image, but there's no way to superimpose it. There's 4 different groups. So the definition of a chirality center is that a carbon has 4 different groups coming off of it. And if it does have 4 different groups, that is called a chirality center. That carbon that has the 4 different groups is a chirality center. You may also hear me refer to it as a stereocenter. So if we look at the examples below, this carbon right here that has a chlorine, a hydrogen, remember the hydrogen has to be assumed, chlorine, a hydrogen, and a methyl group and an ethyl group would in fact be a stereocenter or a chirality center. And I'll let you try the other 2 on your own. How many stereocenters do we see in each of these molecules, if any? So the carbon we're going to be looking at is this carbon right here, and it has an OH, and then of course we have the H. If we take 1 step away, it's a carbon, a CH2. 1 step away, it's a CH2. If we take another step away, it's a CH2. Another step away, it's a CH2. And if we take a 3rd step away, they meet at this center, which is also a CH2. So those 2 groups are actually the same. And so there's symmetry in this molecule. And so this is not chiral. So we call that achiral. There are not 4 different groups coming off that carbon. There are only 3 different groups. What we're going to do is we're going to take 1 step at a time away. And as we get further and further away, the minute it becomes different, then we know that it is a chirality center. Start at this carbon right here. We have the H, so those are 2 different groups. And then we take 1 step away and we have a carbon with an H and an OH and then a CH2. So that is a stereocenter. Now, if we take a look at this carbon right here, of course, we have the OH and the H, so that's 2. And then we take 1 step away, it's a CH2. Another step away, that's a CH with an OH. And so this is also a chirality center. So this is going to be 2 chirality centers in this compound. If we look here, I'll do 1 more for you, and then I'll let you try the last one on your own. If we look at this carbon right here, this is a CH3 and a CH3, so this is not a chirality center. If we look at this center right here, we have a CH3, we have an H, we have a CH with a CH3 and a CH2, and then we have a CH with 2 CH3s. So I hope you see very quickly that that is actually stereocenter. There's not symmetry, and so those 2 groups, this one and this one, are different. So this is a stereocenter, this is not. And if we go to our 3rd center right here, we have a CH3, we have an H, so that's different. And then we have an ethyl group, which is different from this group right here. So this is in fact a stereocenter. So in this compound, there is 2 stereocenters shown there. And I will let you try this one on your own. I'm also going to let you try this one on your own. There will be a question like this on the test where you have to identify all the stereocenters in a large organic molecule. So remember that enantiomers are 2 molecules that are mirror images of each other, but are not superimposable. Therefore, they are not identical. Only a chiral compound can have an enantiomer. So here's a chiral compound. We have fluorine and a CH3. Of course, we have a hydrogen and then an ethyl. So those are 4 different groups. And so this is a chirality center. So you can draw the mirror image in a couple different ways. One way is to just literally draw the mirror image. So we have the ethyl group here now, the chlorine still coming out, the methyl group there, and the H going back. And so that is an enantiomer. The other way you can draw the enantiomer is if you draw the same skeleton, but you switch the configuration. So that Cl, instead of coming out of the page, instead of being a wedge, we make it a dash and we bring the hydrogen towards us. That is another way to draw an enantiomer, and both of those are totally correct. Here's 2 enantiomers, and here's 2 enantiomers. Down here, we'll see an example where they are not enantiomers, because look, this is a CH3, this is a CH3, so there's a plane of symmetry in this molecule. This molecule would be superimposable on its mirror image, meaning that it's the same molecule. So lastly in this video, I want to talk about how we're going to name these stereocenters. And the way that we do that is using the designation R and S. So we look at an enantiomer and we figure out whether it is named R or S, and we put that at the beginning of the name. And the way that we're going to determine R and S is the Kahn-Ingold-Prelog system, and that is the CIP system, just like we did E and Z in double bonds. This system relies entirely on atomic number. The way that we determine R and S for any given compound is we're going to prioritize the 4 groups in terms of atomic number. Once we arrange the molecule so that the lowest priority group faces away from you, we want the lowest priority group to be a dash going away from you, you, where the 3 highest priority groups are going to be coming at you. And I think about this almost like a steering wheel of a car. You're going to take those 3 top priority groups and number them according to atomic number 1, 2, 3. If they are in a clockwise direction, then that is going to be R. And if they are in a counterclockwise direction, that is going to be S. I cannot stress enough how valuable model kits are going to be in this chapter as well. Remember, R and S are solely for naming purposes only. It is just chemist's way to determine which way the stereocenter is. Here's an example. Here's our stereocenter right here. The bromine is coming at us. The hydrogen is going away from us. The hydrogen would be the lowest priority. It has to be. It's got the lowest atomic number. So if we take the 3 groups that we have left, we have a bromine, we have a carbon, and we have a carbon. And so there's a tie. If we look at each of these carbons, this carbon has 3 H's, and this carbon has a C and 2 H's. This one actually wins. Bromine, the highest atomic number, is going to get 1. This propyl group is going to get 2, and this methyl group is going to get 3. If I connect the dots in order, I do 1, 2, 3, and that is clockwise, and so that would be R. For this example right here, we have the hydrogen coming at us. In my mind, I just figure out what the configuration is, and then I switch it. I'm thinking about looking at the steering wheel from the column of the steering wheel. In this example, with the hydrogen coming at us, I figure out the R and S, and then I switch it, because remember, we want number 4 in the back, but in this case, number 4 is right in the front. So we have chlorine, oxygen, and carbon. Chlorine has the highest atomic number, oxygen has the second, and the carbon has the third. So if I'm going to connect the dots, this would go this way, which looks just like clockwise, except for remember, number 4 is coming at us, and so that's going to actually become S. So the configuration of this compound right here is S. So when H is in the back, you're golden, just figure it out. If H is coming towards us, figure it out and switch it. If groups that are attached are similar, it can be a little tricky to prioritize. For example, shown here, here's our chirality center. We have oxygen and hydrogen. Obviously, those are easy, but if we have carbon and carbon, right? This carbon right here has a carbon and 2 H's, a carbon and 2 H's, so they're still tied. We need to take one more step out, and if we look there, we see here that the carbon on the left-hand side has 2 carbons and a hydrogen. So that is actually going to win. That becomes number 2, and that becomes number 3. And so in this case right here, it is counterclockwise S, except H is coming at us, so we have to switch it to R. And one little note, the priority is based on the first point of difference. Here's an example right here. We take one step out from this chirality center and we have 2 carbons, so they are tied. However, even though this is a much bigger group, the fact that this one right here has an oxygen, which has a higher atomic number, means that this one right here is the higher priority. When we are looking at examples where we have a double bond, here's our chirality center. We take one step away, we have a double bond to an oxygen. We have one step away, we just have a carbon. One step away, we have a carbon. One step away, we have a carbon. They're all 3 tied. However, when we have that double bonded oxygen, it counts as 2 single bonds to oxygen. The way that I determine the designation of R or S in a compound where the 4th priority that's supposed to be in the back is actually in the plane of the paper, the way that I do that is I actually switch them. So I do not do what the slide is telling us to rotate the molecule, but I switch them. You may read through this and think that rotating it is better for you, but this is how I do it. I switch the molecule. In my drawing, I switch. So I just move the 4 to where the 3 was and the 3 to where the 4 was. So I draw it this way. So now my 4th priority is in the back. I determine whether this is R or S. And then at the very end, when I'm all done, whatever answer I get, I switch it to the opposite. By doing this right here, I am drawing the enantiomer. And so if I'm drawing the enantiomer and figuring out the designation of the enantiomer, When I'm all done, I have to switch it back. We'll do some practice problems in class on these. Here's a summary of CIP rules. Identify the 4 atoms directly attached. Assign priority to each atom based on its atomic number. If there is a tie, then you have to move 1 step away from the chirality center. So you walk away from the chirality center. Remember, double bonds are treated as 2 separate single bonds. And then ultimately, we need to put number 4 in the back. And then finally, we determine clockwise gets R, counterclockwise gets S. And then I just want to remind you that when we figure out R or S, it becomes that very beginning of the name. Remember, I promised you we talk about stereochemistry in chapter 5. Here we are. R and S goes at the beginning of the name. It goes before the substituents, before the parents, before the unsaturation, and then before the suffix for the functional group. It goes at the very beginning. Cis trans goes at the beginning. R, S goes at the beginning, and E, Z goes at the beginning.
Quick summary: if H or your lowest priority is going in the back, figure it out, you're good. If the lowest priority one is coming at you, figure it out and switch the answer to the enantiomer because you're looking at it from the back side. And finally, if the lowest priority is in the plane of the paper, draw a new molecule where you switch it and put it in the back, figure out the configuration, and then you switch it to the other configuration because by drawing the new molecule, you made the enantiomer.
Again, so many things in organic chemistry. What we really have to do is practice. Good luck.